Welcome to Chapter 15, Air Pollution and Stratospheric Ozone Depletion. This is Mr. Cloud coming from North Belmore from my home, and we're about to discuss a quick topic in Chapter 15 called Ozone Depletion. So let's get right into it. What you see just above my picture, guys, is a photograph of the ozone hole over Antarctica in 2006. Now, what's been pretty good since 1987 is since we discovered this ozone hole, the hole itself has been decreasing and shrinking in size since the passing of the Montreal Protocol, which many nations came together and decided to reduce the emissions of ozone-depleting gases such as CFCs, and we've seen the ozone rebound. What is this lesson all about, guys? Well, this lesson is all about some misconceptions about ozone depletion itself, and I want to talk about the actual process of how ozone disintegrates within our stratosphere, and talk about the actual chemical processes that go into that. So first things first, let's get into common misconceptions about ozone depletion. All right, number one, when I'm grading tests and quizzes on air pollution, one of the most common misconceptions is that someone will say, ozone depletion is caused by the release of greenhouse gases into our atmosphere, such as carbon dioxide. That is not the case. Ozone is disintegrated due to chlorine and other chemicals getting into the stratosphere, breaking down ozone. All right, the most common is chlorofluorocarbons. Chlorine acts as a catalyst to breaking down O3. All right, greenhouse gases, the release of them do not cause ozone depletion. Keep in mind, guys, that chlorofluorocarbons themselves are actual warming gases. They have a much greater warming potential than CO2 does, but I would say concentration of CFCs in our atmosphere is measured in parts per billion or so the volume is pretty low. So in terms of climate warming, they're pretty minuscule, if you will. The second, all right, the difference between tropospheric ozone and stratospheric ozone. The conversation we're having today is highlighting stratospheric ozone, right? That's the good stuff. We needed to absorb that UV. Without the ozone layer, life itself on Earth would have never evolved. Super important. Tropospheric ozone is that secondary air pollutant that's caused by photochemical smog. If you inhale it, it's an irritant to the respiratory tract. It's not good. All right, tropospheric ozone, stratospheric ozone, two separate things. This conversation is about the disintegration of stratospheric ozone. Let's get into the physical process of that now. Okay, so ozone thinning, we discovered it happening in the late 1980s. We discovered the hole over Antarctica. And what I want to do is show you a short video clip on how ozone remains in steady state within the stratosphere. However, the addition of ozone-depleting chemicals has dramatically affected that. All right, and we were able to pinpoint what was going on and pass legislation to help slow it. But first things first, let's get into the chemical process. So I'm going to see a quick video right now. This is from PBS Learning Media. It's a great little clip on ozone and ozone depletion itself. Okay, so I'm going to sit back, watch a little bit, and I might comment once or twice as this goes on.
Ozone is O3. In other words, the ozone molecule is made up of 3 oxygen atoms. Ordinary oxygen is O2. High-energy ultraviolet radiation in the stratosphere breaks oxygen molecules apart, forming 2 separate oxygen atoms. These oxygen atoms are highly reactive, and they quickly join nearby oxygen molecules to form ozone. Stratospheric ozone protects us because it efficiently absorbs ultraviolet radiation. The absorbed UV energy splits ozone into an oxygen atom and an oxygen molecule. The free oxygen atom quickly combines with a nearby oxygen molecule to
I'm not pausing the video just to let you know that ozone remains in steady state within the stratosphere due to UV coming in, ozone absorbing that UV and breaking off of free oxygen. And that free oxygen goes to combine with a molecule of O2 to recreate ozone. And that remains in steady state. But then something happens when we start introducing more and more ozone depleting gases that contain chlorine, bromine, etc. Let's continue watching.
Form ozone. We see that ozone forms, breaks up, and forms again in a repeating process. Because of this continuous repeating process, UV is absorbed by ozone and less reaches Earth. Because ozone is a highly reactive molecule, it interacts readily with nitrogen, hydrogen, bromine, and chlorine compounds. For example, when a chlorine atom collides with an ozone molecule, it steals an oxygen atom to form chlorine monoxide, and it leaves behind an ordinary oxygen molecule. When a free atom of oxygen collides with the chlorine monoxide, the two oxygen atoms bond to form an oxygen molecule. The chlorine atom is thus released and is free again, free to destroy another ozone molecule. This ozone loss sequence is called a catalytic cycle and is a natural process that has always existed in the stratosphere. As a result, one chlorine atom may destroy hundreds of thousands of ozone molecules before it forms one of other chlorine compounds and exits the stratosphere.
All right, let's stop it there. This goes on to discuss how that one chlorine atom can reside within the stratosphere for a really long time. So now let's recap exactly what this video was actually showing us. Okay, so we're going to go back to this. I'm going to jump to this, pop this up, and let's get into it. First things first, the sun radiates energy along the entire electromagnetic spectrum. We see visible light. That's one type of electromagnetic energy. It also radiates infrared, gamma rays, and also UV. When UV comes in to our atmosphere, into our stratosphere, it's going to interact with a chlorine disintegrating chemical. A lot of the time, it's CFC. And that's what you see here. Okay, so the UV will interact with it, and what happens is a chlorine atom breaks off right during that process. You get a free chlorine atom to start attacking ozone. Okay, so the chlorine will then interact with O3 and pluck off a free oxygen atom. All right, O2 is left behind, and what we do is we create chlorine monoxide here. Okay, I'm going to move myself to this side so you can see this. Okay, the chlorine monoxide then will interact with the free oxygen to create O2, so that free oxygen will pluck off the oxygen from the chlorine monoxide. And guess what, guys? That then leaves the Cl, or the chlorine, to continue the process over and over again. Now let's do an overlay with actual text to make it easier for you to see. Okay, so the sun, UV radiation comes in, interacts with CFC. Chlorine blasts off. It then interacts with O3, breaking off an oxygen. What occurs, guys, is that the chlorine atom and oxygen atom join to form a chlorine monoxide molecule. It then interacts with a free-floating oxygen, pops off the oxygen from the chlorine monoxide, and once free, the chlorine atom is up to attack another ozone molecule and begin the cycle once again. I was reading that this process can last for a really long time, and that chlorofluorocarbons can reside, they have long residence times within the atmosphere, upwards of a few hundred years, as a matter of fact. So again, once chlorofluorocarbons are released, they stay there for a while, and this disintegration process can happen for a really long time before the chlorine combines with something else to then be released from our stratosphere. Okay. As a quick aside, guys, last thing I wanted to mention to you is that we can link over, guys, to show you exactly what the Montreal Protocol looks like, guys. This is from, I'm going to slide over the screen a little bit so you can see it, the Ozone Secretariat. Okay, this was passed in 1987, everybody. Here I am down over here. Okay, and you can go onto this website, the UNEP, and take a look at all the um, different parts of the Montreal Protocol. And it goes to show, guys, that we can really affect our atmosphere once we know exactly what's going on. Once we know what chemicals we're releasing, that's affecting normal processes, that we can get together, form legislation, and really get the job done. All right, it's truly a success in that way. So this is Mr. Cloud coming from North Belmar, New York. Thank you very much for watching this video. And I hope this helps you understanding the really complex interactions between chlorine and ozone with our atmosphere. Thank you very much for listening. I'll see you all in class.